Hello, everyone. My name is Reynaldo Michelena, and today we're going to be talking about opinion polls and how the concepts that we learn from opinion polls can bring new insights when we apply those concepts to seismic data analysis. And what I'm going to show here is a technology that is proprietary of SeisPetro. We've been using that for about 15 years since we started the development of this back in another consulting firm that is iReservoir. And in this case, what I'm going to emphasize is in the similarities between what we do and the actual opinion polls. And even though we have presented these techniques several times over the years and we have published about it in different journals, I wanted to take this time to do something that I didn't do before, which was to explain how in detail how the opinion polling concepts are being used in the technique and how the technique differs from other methods that are commercially available. So since we're going to be talking about opinion polls, there is no best way to do it than looking at the results of an actual opinion poll. Here is a poll that was conducted by the company Gallup, a big pollsters with worldwide reach, and they conducted this poll in India. And what they did was that they asked the participants in the poll a very simple questions. Do you agree or disagree with the following statement? So they asked that question, and what they report here are the results of that question. We asked the percentage of people that agreed with the statement. So they report that in 5 different regions in the country. And that's it. Those are the results of the poll. So they have 76% responded yes in the north, 45% responded yes in the south. So as we see these results, we have learned and we have seen that in different places, especially when we see the pollsters reporting results, let's say in presidential elections in TV, that you don't trust the results of any poll if you don't see the technical data. So sure enough, this is what Gallup did regarding to this poll, and they report, for instance, what is the geographic, the domain of the poll, which is the geographic location, in this case in India. They also report was what they call subsegments of the population were considered. In this case, what was age and income, and we're going to be discussing this again later to see the analogy when we analyze seismic data, what the equivalent of the subsegments will be. The sample size for this poll was 2,100 individuals, and the margin of error that they report for the poll was about 3.5%. And that was assuming a confidence level of 95%, which means that if they go back to the field and they repeat the poll, there is a 95% chance that they are going to get the same results. This is remarkable that for a country of this size, with the population of about 1.4 billion people, they can get meaningful answers that can help understand attitudes of the population with only a fraction, 10 to the minus 6 individuals, or a fraction of the whole population. So it's fairly remarkable. Also, what they report is that they oversampled one population that was the urban population, but then they don't say anything about what kind of methods they use to weight for other areas that were not oversampled, like the rural areas in the country. So this is the technical data, but when you look at the individual results for the different regions and you wonder, well, where do these results come from? They come from a simple ratio of two numbers, and Gallup didn't report these numbers. It was just me that made these numbers up for the sake of the explanation. But they should have these numbers somewhere, but they didn't report them. And that number, that probability that they assign, let's say, to the north here, comes from a ratio of two numbers. In the denominator, they have the sample size, which is the number of people that participated in the poll. And in the denominator is the answer of the number of people that responded yes. So we see that in different regions, probably different, the sample size was different. And here, for instance, in the eastern region, we see that the sample size is 100 compared to, let's say, the northern region, where the sample size is 550 people. So we know that when we apply the definition of probabilities to estimate these fractions in each of the regions, we assume that the sample size has to be large. So what this is saying is that in terms of the reliability of these estimates is going to be more reliable the more people we have. So it's going to be more reliable to the north than this result in the east. Okay, so this is the opinion poll that we use as an example. I'm going to keep referring back to it as we start with the analogies of seismic data analysis. So in this presentation, first of all, I'm going to pose the problem of rock typing as an opinion poll. That will be the first task of the presentation. And then I'm going to be showing examples of facies mapping results based on polling concepts. And the examples will be for unconventional oil, conventional oil, unconventional gas, and conventional gas reservoirs. And also, I'm going to be discussing in the middle of the presentation what's different about this approach compared to commercial implementations of facies probability analysis from different vendors. And I'm going to discuss also the advantages and limitations of this approach. Okay, so now we are ready to start making these analogies. The first one is that we need to define what is the domain of our analysis. And that domain is going to be the seismic attribute cross plot. And in this case, we have two attributes, A and B, and we do a cross plot of those attributes. And these attributes are extracted from a 3D cube where we did some computation to generate this attribute. So each of these points that you see in the cross plot is basically one point that came from the whole 3D grid. So this is basically our country. And what we do is that we now separate this country into states, similar to the states that we saw in the map before, the survey in India. But the difference here is that we are going to draw states that they're not going to have crooked boundaries, because we want to simplify, of course, the computation. So we're going to draw states that are rectangular. And as I said, that will help simplify the counting that we need to do. Okay, so we have the domain of the survey. The next question is, well, what is the sample? And to answer that question, we go to an example from an unconventional oil reservoir that we did some work several years ago. And the sample are the attributes extracted along the well path and in space domain. So here we have two attributes in a grid, attribute A and attribute B. And then we have in this case, 8 horizontal wells. And what we do is that we extract these attributes along those horizontal wells, attribute A and attribute B. And at the same time, we generate along this horizontal wells, we generate a target flag or a flag that indicates the target rock. And we're going to refer that as the question later in the presentation. And in this case, the only information available along these horizontal wells was a gamma ray. So we generated that target rock flag basically using the cutoff of the gamma ray, the target rock gamma ray less than 70, and what we call the background rock is for gamma ray greater than 70. Okay, so this is the sample, and then when we go back to our domain, our cross plot domain, and then we see where our sample falls. These are the points now that we extracted along the well path. Okay, so these are now the individuals that are going to participate in the poll. And I'm going to draw a region here around the points that we extracted from the well path, just to keep that as a reference for future, to show other results in a couple of slides. Okay, so we have the sample, and the next thing we need to do, like in any poll, is to ask a question. And in this case, the question is very simple. Do you vote for target or do you vote for background? Okay, and then the answer to that question is in basically the facies flag log that we generated along the horizontal wells. And here we're coloring each individual by whatever they answered. So some of them, let's say in this region of towards the center or northeast, they tend to think that they voted for target rock, whereas in this region towards the west, there is more of a mixed in the votes between target rock and background, more overlap in the properties of the two classes. Okay, so something that is different in this context of seismic data analysis is that we are going to assume that all these samples, they always tell the truth. It's not that what happens with pollsters, that sometimes they're afraid that the individuals that participate in polls, they are going to lie. In this case, they don't lie. Our samples don't lie, which is like an expression of the assumption that we always make, that things that well data is treated as hard constraints. Okay, that means that no errors are present in the generation of these flags. Okay, so now our poll has been conducted. We have the results of the poll, but now we need to analyze it. We need to analyze to understand what this population was telling us. And with respect to this point of how we analyze the data, let's consider a zoom-in version of the previous cross-plot. Again, we have attribute A and attribute B, and here we have our, in this case, square states. And what we do is that exactly the same way we do with opinion polls, we simply do counting. Applying basic probability definitions. So in each cell of the cross plot, we count, let's say, how many points there are, which is the size of the sample. And then we also count how many individuals answer yes to our questions, or how many individuals voted yes in this case, for the target rock. So in this cell, or in this state, 5/9 individuals voted for target rock. In this other cell or state, 2 out of 7 voted for target rock. So this is one of the pieces of information that we can extract. And when we see this definition of how we compute this probability based, as I said, on the probability definition, we can interpret the probabilities as the net to gross of the corresponding cross plot cell. So that's the interpretation of the probability. So this is one of the pieces of information that we can extract from the cross plot. And the other is a measure of reliability. We know that the larger the sample size, the more reliable the results will be. So in this case, the results that we obtain from these cells based on 9 samples will be more reliable. Let's say that the results that we obtain from these cells that has only 7, and even much more reliable than results that are obtained from this cell that has only 1 individual. So this will be totally unreliable, because this is similar to saying that if you ask one person in one state who they are going to vote for the presidential election, and then you base the results, you extrapolate that to assume that that will be what the rest of the population in that state will answer. So that is totally unreliable. So, and that's a number that we can also extract from the analysis, from the counting in the cross plots. So when we do that computation of the probabilities, and we go back to our cross-plot domain, we have again attribute A and attribute B, and in this case, the color is the probability that we have computed using basic probability definitions. We see here, as expected, that the Northeast region here, let's say in this cross plot, all these states, they voted for target, whereas in this region towards the west, there is more of a mixed response. You may wonder, well, what happened here in this area where that is outside the point samples by the well path? And what we do is that when we do this analysis, we don't use a fixed number or a fixed size for the cells or the states, but we do variable sizes to make sure that in regions of the cross plot where there was originally no samples, we end up getting a sample. It will be lower resolution, but nevertheless, we will be a sample. So for instance, we start by computing probabilities in 4 big regions, and then we start enhancing the resolution as we proceed. So that's how we can put points outside the areas that were actually sampled by the wells. Okay, so when we take these probability results now back to space domain, this is what we get in this example from the unconventional oil. We get the probability of the target. So here we have the 8 horizontal wells, and the colors here are the probability of the target expressed as a percentage. We also get the sample size. And as we can see, the sample size can vary. In this case, the scale goes from 100 to 400 samples. So it varies across the area, which means that not all the points are equally, let's say, well calibrated with the well information that we have. And then when we combine these 2 results using a formula that I will show in the next slide, we get the margin of error. And the margin of error is just quantity that we add or subtract to the probabilities that are being estimated. So for instance, if the probability here in this map, if we have a value of, let's say, 40%, and the margin of error, let's say, is 2%, that means that the ranges of possible probabilities will be between 38 and 42%. Another way to use the margin of errors is to prioritize areas based on the uncertainty that we have in the answer. So for instance, we see here 2 areas that have high probabilities, but then when we look at the margin of errors, we see that this area in the center has a lower error compared to this area towards the west. So in terms of prioritizing, we can say, okay, if we're going to drill new locations, or if you're going to constrain other modeling processes using these results, we're going to give more weight to wherever we have the smaller error. So how do we calculate this error? The margin of error, as I said, is the probability that we estimate plus minus a number. And that number is estimated using this formula, which is a standard formula that also comes from opinion polls. And that formula has 3 parts. It has this constant that is called the z-score. And it's the confidence interval. It corresponds to the confidence interval that we're going to assign to the error. It has the probability that we are estimating, and it also has the number of samples. So this is saying that as we increase the number of samples, the error decreases as we expect. But also it also is going to decrease as the probabilities either they are close to 1 or close to 0, which means that they are well separated in the cross-plot domain, not much overlap of properties. So that will also contribute to reduce the error. Typically, what opinion pollsters do is that they assume that this P is always 0.5. So they basically generate an error estimate that depends only on the number of samples, because they assume I would say, the worst case scenario for P. Okay, going back to results from a different area. This is a conventional oil example in offshore Brazil, where we wanted to map 4 different phases: the porous limestone and the porous dolomite, where the oil was deposited. There was also a tight fracture rock and other phases, a combination of different rocks. So here are the results for 6 wells. This is what we show for each of the wells. So here we have a gamma ray curve in the first track. We have the phase flags on the second track. And then the third and the fourth is where I want you to pay attention to. The third track is the proportion curve of the phases at that well. Is basically to upscale those phases to something that is comparable with the seismic. And then the fourth track is the proportion curve that was estimated from the probability analysis that has been explaining. So you compare here the third and the fourth track. So, and can see that in some places it does a very good job in predicting the phases. Even the one that are not too abundant. In this case, like the dolomite, in some cases, the seismic does a very poor job. It gets confused with the facies. In this case, it classifies as other, something that was supposed to be tight. But then you can examine the agreement between what is expected and what we estimated from the seismic in a problem that was particularly difficult because there was a lot of overlap in the response for the different attributes. Okay, so what we consider this result was to be mainly useful. So we decided to continue using this for other parts of the model building process and decision making for drilling new wells in the area. Okay, so you may be wondering now, okay, how do we explain in more detail the differences between this approach and other approaches that are commonly applied in other commercial applications? So what's different about this approach? The difference of what we do compared to other commercial applications can be summarized with basically one word. This approach is called frequentist, as opposed to the more commonly used approach for facies probability analysis that is based on Bayesian formulation. And to better understand those differences, we have to go to the Bayes theorem, and that's the very famous Bayes theorem that relate what is called the posterior probability of, let's say, the target for a given attribute with the parameter that is called the likelihood, which is the conventional probability of the attribute for a given target, and the prior of the target. So that what the Bayes theorem is doing is that it's basically modifying whatever preconceived notion you have or whatever belief you have in your prior and generated a posterior result that is basically the modification of that prior. But when we look at this term on the left, we have to remember that that is basically a conditional probability of the target in the attribute range. So we can estimate this number, yes, using the Bayes theorem, but also we can estimate that simply applying probability definitions to obtain this conditional probability of the target in the attributes range, which is what is commonly done then in opinion polls. And then when we do that, we don't need a prior. We don't need to model anything before we do the computations. We base the whole analysis on the data that we have. So going back to the differences between what we do and other approaches, as I said, is frequentist, not Bayesian. The approach is entirely data-driven. No prior model is needed. We don't need to model also any PDF probability density functions before we do the analysis. And it basically, everything boils down to the difference between the two approaches on what is based on the data that you have versus what should be based on your prior knowledge or prior ideas of what should be the answer. Okay, so with this formulation, then it allows us to do other things that, at least in the common implementations of the Bayesian approach, are not available, which is that we can use now wells that only have, let's say, the facies flag. We don't need any other type of information. And basically, we can use any attribute that we think is related to what we're looking for. And we use attributes extracted along the well path. And we don't need to have like the equivalent of the attribute that we are analyzing also represented as a log along the well path. The result of the analysis is the probabilities, also the margin of errors, and reliability estimates. And something interesting also is that it allows us to use multidimensional attributes. It doesn't have to be two, which is equivalent to the concept of segments of the population that we discussed at the beginning. That is basically adding additional access to the cross plots to better analyze the data. So in this example, what I show is one application where we, in an unconventional gas reservoir, where we have 5 input attributes, 3 from P-wave data, from inversion of P-wave data. So we have acoustic impedance, shear impedance, and density. And also we have 2 more attributes from the inversion of multi-component data. So what I show here for one well is these results. The first track is the original sun flag. The second track is the average of this flag. And then what you see in the remaining tracks is the combination, let's say, of AI and impedance, the probabilities that came from the combination of, let's say, AI and impedance, AI and density, shear impedance and density. And so you compare these tracks, each of them with the average sound flag. And here in this track where it says 3, we're calculating the probabilities using simultaneously acoustic impedance, shear impedance, and density. And you see that that's the best we can do with conventional seismic data, as it follows relatively well the variability that we see in the well. However, when we bring the multi-component inversion results, so for a total of 5 attributes, we get a much better result that much better resembles what we expect at the well. And the reason is that in this case, the multi-component is bringing additional information related to the anisotropy of the sands that wasn't present in the conventional data. Also, I show here what is the original inverted AI trace and how the probability results, they tend to enhance the resolution, simply because we're working in grids here that has a very fine resolution that is much closer to the resolution of the well log. Okay, so far we have been discussing results in the continuum, which are the probabilities, but many times we were interested in going back to the discrete domain and to look at the actual phases, the discrete phases in space. So how do we do that? And there are different ways to do that. We can either pick a winner among all the different probabilities. We can also draw random classes from probabilities and errors. We can calibrate these probabilities using different cutoffs until we honor the log phases data. We can also perform geostatistical modeling constrained by pole results. We've done that in the past, but I'm not going to show that in this presentation. Or we could use rock physics concepts to classify values that are, let's say, extreme, but they are rare. So for instance, if we are in one area where we see large values of impedance and density, so we can say, okay, probably these values correspond to anhydrides that are present in the area that we know are present, but we are not sampling them with the wells we have. So here is an example of that, how we applied that concept of going back to the discrete domain. This is an example from a conventional gas reservoir where we have 4 phases. A phases, which is gas, a transition phases, which is probably residual gas, water, and the background. So in each of this well, we have 3 tracks. The first track are the original phases, and the other 2 are discrete phases generated from the probabilities using different methods. Here, when we say the winner, we pick the largest probability and we simply assign that to the phases at that particular depth. And what we see is that even though we agree reasonably well with respect to the phases in the upper part, then we are missing here the water phases. We have too many samples for the backgrounds that when we pick a winner, we don't see the water. But then when we apply this calibration of the cutoffs of the probabilities, trying to reproduce what we see at the wells, then when we examine the results of that calibration, we see the water back. Again, when we do that comparison for other wells B or C, we see that here is the original. The winner has less water. When we calibrate, we get the water back, and it is particularly clear here in well C that is basically water. But then when we pick a winner, we're basically missing all the water. When we look at these results in map view, this is how it looks. When we pick a winner, we have a fairly continuous pool of pay. But then when we start doing stochastic simulations using generating random models that sample the probabilities and the errors, we start seeing that probably this pool is not so continuous. We start seeing transition areas in the middle. But then when we look at the calibrated results, we better see the patches or probably patches in the distribution of the phases. Okay, so now when we examine the errors in these phases, the main conclusion is that we don't estimate the different phases with the same error. So for the pay and the water phases, the errors are around 6%, but for the transition phases, the errors are much larger, and for the background facies that is the one that is sampled the most, then they have a much smaller error that it is less than 2 or 3%. So we're approaching now the end of the presentation. We still will have to talk about the limitations of this approach. So it's a good time to kind of step back and say, okay, what is an opinion poll? An opinion poll is similar to what cooks or chefs do when they taste a big batch of soup that they are preparing before they send that to a restaurant. And what they do is that they try a little bit. And so a spoonful is enough to know how the soup tastes. They don't have to eat the whole thing or have even a plate. It's just a small sample what they need. But there are caveats with this approach. And is that if there are different ingredients, and I'm going to quote Professor Kevin McConway from a statistics professor from the UK, and he says that it is important to stir up your soup and get a sample that includes all ingredients in proportion, and that's the keyword, not an isolated lump. So that tells you right there where the limitations are, that if you don't sample your population in proportion, then you're going to get into trouble. So what is the limitation of the method? The limitation is basically sample bias. Like in any other opinion poll, and that translates into that one type of rock is more likely to be sampled than others, and because it's very hard to get adequate proportional sampling with well-logged data. And this is not only a limitation of this approach; it's basically a limitation of we have to address every time we calibrate seismic data. That in polling terms, that has like two kind of negative consequences for the polling results. One that is called the prejudice, and the other one is called the favoritism. And the prejudice is because sometimes we avoid areas to drill, we don't drill them, or sometimes we on purpose want to drill some areas. So those two biases, they will impact negatively the results. And what happens is that those results, they will tend to favor the majority. Okay, and of course, if we have small samples, all these problems will worsen as the number of samples decrease. Okay, how do we compensate for these biases? Well, calibration is very important. We calibrate the discrete facies to well-logged data, as I showed in the previous example for the conventional gas reservoirs. We have to use physics and rock physics concepts as well, and make sure that the results make sense. We have to check for the geomorphology and make sure that the results make sense also from the geological point of view. And we could also perform more elaborate geostatistical modeling constrained by seismic data and facies proportion curves. Okay, so this is it, basically, what I had to say. Now, to summarize, what we have seen is that these opinion polling concepts, or the frequentist approach, allows the estimation of probabilities, errors, and reliabilities. We can use any seismic attributes related to the target rock. We can use wells that only have facies flags with no other log data. So those wells now become available to us. And also we can use more than 2 attributes. It doesn't have to be 2. We have seen also that there are different ways to go the discrete facies from the continuous probabilities, and those ways are basically the winner, stochastic, calibrated, or geostatistical approaches. And mainly limitation of the method is sample bias, like in any opinion poll, but that can be addressed in different ways. And what we have seen with a different example is that the methodology has proven useful in a variety of geological settings. Okay, so that's all I have to say, and I thank you very much for your attention.